So the idea of limits and continuity. Basically what a limit is, it's helping you describe how a function behaves, most usually at points of discontinuity. So for example, our hyperbola over there would be interested in knowing, well, okay, we know x can't equal 0, but what happens as it gets really, really close to 0? And of course there's two different answers for that one, depending on whether you're coming from the positive side or coming from the negative side. But we're interested in those sorts of things so we can draw the graph and things like that. So there's this sort of idea. We say, well, what is the limit of a particular function as x is approaching a certain value? So in other words, as we're getting closer and closer, as x is getting closer and closer to a, what's the y value doing? Okay. Now, the first one where it's just x approaches a, that's all you'll ever really be asked in a test or anything like that. This other one is what I was saying is about, if I was approaching it from the negative side, then I'd write a with a negative there. So that's what's happening as I approach it from the negative side. So if I had an absolute value curve like this, now as I approach 1 from the negative side, well, the y value is approaching 0. Okay. And I've got a graph over there. If I was approaching that one from the negative side, but this time as I approach 0, the y value is approaching 4. If I have a look as it's approaching from the positive side, well, over here on my absolute value graph, I get the same answer. It's still approaching 0. Whereas the one on the right-hand side, if I approach 0 from the right-hand side, it's approaching 6. Now notice it doesn't actually equal 6 because it's an open circle, but it's getting closer and closer to 6. That's a way of defining a continuous curve. If those limits were equal, then we know the curve's continuous. Whereas if they're not equal, then there must be some sort of break or something like that. Now, that's a formal definition, but as I say, in our course we don't really worry about the A from the negative side, A from the positive side. For us, when is it continuous, it's a matter of looking at the picture and going, oh look, there's no break, so yes, it is continuous. So they won't actually ask you to find limits from the positive side and the negative side. They may ask you just to find a straight limit though. So let's have a look at that. Different ideas. Well, one is to simply substitute the number in and see what's happening. So if I've got the straight line there, y equals x plus 7, I want to know for some reason what's happening as x approaches 5. Well, I can just substitute it straight in and we know, okay, it's approaching 12. Sometimes that's not going to work. So another technique we try and look for is to maybe factorise the whole thing and see if there's stuff that cancels. A curve like this one, x squared minus 9 on x minus 3 as it approaches 3, but you'll notice the bottom of the fraction would end up being 0, and you can't have 0 on the bottom of the fraction, so that would be an asymptote or something like that there. So what's the y value approaching? Well, before we can find out, we'll factorise, and the x minus 3, you'll notice in this one, cancels. And so it would be the same as if I just substitute into x plus 3. And so 3 plus 3 gives me 6. So I know that whatever that particular curve looks like, that it would be approaching the value of 6. Now, have a look at my setting out there. Notice, limit as x approaches 3 remains until I actually substitute in. So you've got to write that on every line until you actually substitute that value into it. What would that look like? X squared minus 9. Well, basically it would be the line y equals x plus 3, but probably with just a point discontinuity, I think, on that one. Because every other value you could substitute in. Yeah. Alright, but now we have to define a special limit, and this is the one that we're really interested in. And it basically comes from what we know about the hyperbola. Because how do you substitute infinity into something? I mean, you can't get to infinity anyway, but how do you substitute it in? And you can't. So I think of a graph where I know what actually happens, and that graph is the hyperbola. As x is getting bigger and bigger and bigger and bigger, my hyperbola is getting closer and closer to a y value of 0. So I know that's true because I know what the picture looks like. So using that limit, we can find things like this. Now, to attempt to substitute infinity in would be crazy, because think about it, I'm going to sub in this huge number, bigger than any number that you can think of, and I'm going to cube it. So that's really big. And then I'm going to add 3 times its squared, even bigger again. Plus 2 times this really big number. I'm talking something huge here. And then I'm going to subtract 1. So what? I mean, it's just a huge number. But now I'm going to divide it by 4 times this really huge number, minus 1. How do you make sense out of that? And the answer is, well, you can't. But I can do something quite clever, because the thing I do know is my special limit up here. So what I'm going to do is I'm going to divide everything by x to whatever the highest power is. Because what that will mean is, when I simplify every one of those fractions, x is no longer in the numerator, but it's always in the denominator. And when it's in the denominator, my special limit is telling me, oh, well, that fraction is going to approach 0 when I substitute infinity into it. So every one of those fractions is 0, leaving me with a quarter. So whatever that particular graph looks like, we know as x is going out to infinity, this particular curve would approach the value of a quarter. In fact, it would be the horizontal asymptote. That's another way of finding asymptotes. Now, of course, I can save myself some time by using a little bit of common sense here. I don't have to physically do that. If you have a look at what I've ended up with. Remember, the key was dividing by the highest coefficient of x. What am I left with? 1 on 4. Have a look at the original question. How does that match my question? What pattern do you notice there? That's the word you're looking for, yeah.
X cubed.
Okay. Remember, we decided we were going to divide by x cubed. We've been left with the coefficients of x cubed. Well, that makes sense because, of course, x cubed divided by x cubed is 1. So I can save myself some time here. I can look at this one and say, well, I'm only going to be left with the coefficient of the highest power, which, again, in this case is x cubed. So I know I would be left with 0 on 1. So this one would approach 0. How about this one? Really doesn't matter. I can make it look difficult by throwing in big numbers, but it's still the same idea. The highest power for that one is 7. So if we just look at the x to the power of 7 and its coefficients, this particular graph would be approaching 1/3. Okay, well, what about this one? X cubed plus 2 on x squared plus 1. Highest power again is x cubed. I'd be left with 1 on 0, but 1 on 0 is undefined, and so that probably means this curve is going off to infinity, because infinity is not really defined. If you're ever unsure, remember you're dealing with big numbers, so if you're unsure, plug in a big number into the function, then plug in a bigger one, then a bigger one, and you start to find out what it's getting, where it's heading. If your answer's getting bigger and bigger and bigger, you must be going off to infinity. If your answer is approaching a constant number, you will notice, and things like that. So substitution is still a way of working out a limit as well. So horizontal asymptotes we talked about before. So if I wanted to find the horizontal asymptote of this one, well, it's like saying, what's the limit as x approaches infinity? Well, if I was to expand that out, I've got x squared plus x minus 6 on x squared minus 1. So it would turn out that my horizontal asymptote is 1. See, if you were to do the polynomial division here, you'd end up with 1 plus something on x squared minus 1. So it's another way, as I say, of working out your horizontal asymptotes. It will only be a horizontal asymptote when the power of the numerator is, and I'm going to leave a word out there, than the power of the denominator. What's the word? The same? Maybe. The same is certainly true. Less. Or would it be more? So really they're our choices, aren't they? Less, more, the same. Well, we certainly know when it's the same, we'll end up with 1. What happened here? When it was more, we ended up with a problem. I think we had one. Did we have one where it ended up being 0? Yeah, here. So when it was less, we ended up with 0. So the x-axis was the horizontal asymptote in that one. So yeah. So as long as the numerator is less than the denominator, so the order of that one, we know we'll get a horizontal asymptote. If that order is less than, it will be the axis. If it's equal to, we can look at the limit. If it's greater than, it's probably heading off to infinity, going off that way. Okay. Now, oh, there we go. So our horizontal asymptote, y equals 1.